In this video, we're learning a new integration technique called trig substitution. This technique is very effective mostly when the integrand f of x contains sum or difference of two terms, for example 4x squared plus 9 or 16 minus x squared in the denominator or raised to some power. The idea is with some trig substitution we'll be able to turn two terms like this into a single term. Preferably square if these guys are under square root sign. So not only can we get rid of square root sign, but also turning two terms into one term. And then when those kind of expressions appear in the denominator, by turning two terms into one, it would help us more easily deal with a fraction. Alright, so what kind of trig substitution are we talking about? Well, depends on the sum or difference and also the order of terms involved in the sum or difference. We try to utilize some trig identity. Say we have 16 minus x squared. We want to turn this into a single term with help of some trig identity. Well, think of this as a 1. In trig, we know 1 minus sine squared equal to cosine squared. It makes sense to hope to have sine squared here. But in order to apply the exact identity, we have to match the 16. So this term better be 16 sine squared. Now, if let's see, x squared actually is 16 sine squared, then this will become 16 minus 16 sine squared. This is a 16 matching 16. With that, we can factor 16, leaving us exactly the combination we wanted to apply the identity. So this way we get cosine squared, one term, and most of the time it's a square. We will be able to say get rid of a square root if those two terms appear under square root sign. Alright, so the principle behind this technique is according to whatever structure, we try to think of some trig identity to come up with our substitution. So in this case, then we would be using x equal to 4 sine theta. That would be a new variable. Sine theta. That would be the trig substitution we would use for this kind of difference. Alright, we will examine 4 different kind of sum or difference of terms. First, say we have in general a squared minus u squared, like the one we just discussed. For this, our thinking is like here, u squared better be a squared sine squared theta. This way our substitution is u equal to a sine theta. Then we just plug in, at least this difference can be turned to a single term, like that. Next, a squared plus u squared. Well, this is sum of two terms. So what we have in mind now is another trig identity that says 1 plus tangent squared equal to secant squared, one term. So in this case, we hope u squared to be a squared tangent squared, the a squared matching the a squared there again. So the substitution we want in this case is a times tangent theta. Another structure we often encounter is u squared minus a squared. Now this is not necessarily the same as that, because under square root we cannot change one to another, so we need to discuss them separately. If it's not a square root, sometimes we switch order with maybe a factor of -1. That may not be a problem. It could be a problem if they are under square root sign. So let's see what we do. Just say we want to keep this order. For this time, we will try to use a trig identity that says secant squared minus 1 equal to tangent squared. So the u squared here must be a squared secant squared for this whole thing to work out. So if you plug in, you can see here a squared matching a squared, then you factor out the secant squared minus 1 tangent squared, it will work out. So in this case, the substitution is going to be u equal to a times secant theta. Alright, so these are the 4 cases. Oh, 3 cases. 4. Why 4? 3. 1, 2, 3, right? Now, so the identity we try to use is 1 minus sine squared equal to cosine squared, and the 1 plus tangent squared equal to secant squared. Secant squared minus 1 equal to tangent squared. So given an integral with an integrand containing any of those guys, so we try a trig substitution. This integral would become a new integral involving theta, d theta, right? This will be a trig integral with the trig everywhere, power trig, whatever. And we learned to evaluate this kind of integral before. Say we find the answer with the theta. Case 1, case 2, sine, cosine combination, secant tangent combination, whatever case we worked out this kind of integrals before. Well, this is not the end. Although integration is done, To go from integral involving x to integral involving theta, we utilized one of those substitutions. So at the end, we need to turn this back to an answer involving x. This is generally the steps we would go through to evaluate integral using this trig substitution technique. There are three parts. So first, we try to come up with an appropriate trig substitution, transform integral to a new integral in theta. And this new integral is a trig integral. And part 2, we evaluate this like before. Part 3, we turn the variable back to x. Now, we kind of discussed how to decide which trig substitution to use. Depends on whether it's a number minus a square, or square plus a number, or a square minus number. That's this part. So we have to just plug in, do the substitution, whatever involved. In part 2, where they talk about it, this kind of trig integral, depending on the combination, depending on the trig involved. Sometimes we use a substitution method. Sometimes we use a formula, a reduction formula, direct formula, and so on. And the third part, most of the time we need to rely on a trig. Most of the time we need to rely on a triangle, which is based on the trig substitution involved. For example, if we use u equal to a sine, this basically says u over a equal to sine. With that, we can construct a right triangle. Suppose this angle is theta. The substitution says sine theta is u over a, but definition of sine is opposite over hypotenuse. Now, from Pythagorean theory, we can calculate the third side, the bottom side in this triangle. So a triangle is constructed based on the substitution. Now, if we want to turn this thing back to an expression in original variable x, suppose u equal to something times sine is involved. So now here, depending on what trig involved, when we integrate the trig integral, the answer could contain all kinds of trig, sine, cosine, tangent, secant, whatever. But that's okay. From the triangle, we can find expression for any trig. Sine, of course, is u over a. Cosine would be adjacent over hypotenuse. Tangent would be opposite over adjacent, so on. Cosine is use the variable u here. Then here it would be just x. So we would have x there, x there. All right. So based on each trig substitution introduced, we can accordingly construct a right triangle to help us determine expression for any trig involved. Now let's complete the table. Suppose we use u equal to tangent. So here this says u over a equal to tangent theta. This time when we construct also a triangle, assuming this angle is theta. Doesn't matter you call this as theta or this is theta, because you're end with the same proportion for the same trig function. Okay, so tangent, what's tangent? Tangent is opposite over adjacent. So, okay, Pythagorean theory says the hypotenuse would be a squared plus u squared. Okay, we'll be able to find the expression for any trig based on the triangle here. The third substitution, so u over a is secant. U over a is secant. Now if this angle is theta, secant is u over a, so cosine is a over u. Cosine is a over u, adjacent over hypotenuse. And we can again use Pythagorean theory to find this side to be u squared minus a squared. Alright, so those triangles can be useful the last step to turn expression in theta to expression in x and final answer. Now let's see examples. Okay, this is integral involving 4 minus x squared. See, this is what I was talking about. You have a square root with two terms. If there's no simple substitution like a 4 minus x squared equal to u, such expression is very difficult to integrate. Well, let's try our trig substitution. Okay, 4 minus x squared. Let's write it down here. 4 minus x squared. So based on our discussion, we want x squared to be 4 sine theta squared. This way 4 minus x squared becomes 4 minus 4 sine squared. Factor out the 4, 1 minus a sine squared. That's a 4 cosine squared. One term and its actual square pretty much always work out this way. So let's see. With this assumption, x is 2 times sine. Just take a square root. So plug in 2 sine theta for x. So 2 sine theta square, and the 4 minus x squared we already worked out. That's 4 cosine. See, it's the square root of a square. How about that? And the dx, well, with the substitution, let's see, dx is 2 cosine theta d theta. So it's 2 times cosine theta d theta on the side. Okay, you see trig everywhere. Now, how I'm going to integrate this trig? Simplify first. This is a 4 sine square. Cosine, there's a square root, they cancel each other. 2 and 2 square root 4 is 2 cancel out, so it turns out it's actually that. We're done part 1. Integral involving x turn to integral involving theta. Trig integral involving x involving theta. Well, question is, how are we going to integrate this? Let's say the force is constant, more moved out, stay on the bottom. Secant square, sine square. In the denominator, it's difficult to integrate anything in the denominator. Impossible. Anyway, so what's 1 over sine? Let's turn this into a cosecant square. Well, we're lucky. There's a formula for that. It's a negative cotangent theta plus c. Alright? Once you get everything in theta, simplify, see what you have to do. This case, it's actually pretty trivial. There's a formula we can apply directly. So, compared to our general process, this is step 2. Integral of trig, finished up. The answer in theta. So there's a last step. We want to turn this to x, to an expression in the original variable x. We start with the integral in x, so the answer got to be in x. So how do we do it? We got to now come up with one of those triangles. Which one? Depends on the substitution. We don't need to go back to the table. We can just construct the triangle, each every problem fairly easily. So this substitution basically says sine is x over 2. Well, sine is x over 2, so let's say this is theta. Sine is opposite, so x over 2, so this side is x over hypotenuse. Sine opposite over hypotenuse, and this side would be 4 minus x squared because of Pythagorean theory. Just explain this a little bit. Suppose you start say, let's assume this to be y. Then Pythagorean theory says y squared plus x squared equal to 2 squared. So you move x squared over and take a square root, and y equal to the radical there. Okay, so for the triangle, what do we want? We want cotangent. Cotangent is adjacent over hypotenuse. Negative, we move it out. Adjacent over, not hypotenuse, adjacent over opposite. This is hypotenuse, sorry about that. Well, we got our final answer in x. So this simple example shows the kind of work we do in the steps we usually go through. First, come up with the trig substitution to turn this integral in x to an integral in theta, which is a trig integral, and then evaluate, then use triangle to turn theta to x. Let's see another example. Here we have, well, two terms in a sum raised to power in the denominator we better turn this into a single one. So 25 is the number, and this is the guy that's going to become some sort of a trig. From what we've discussed, with the 25 plus the 16x squared, it's a sum. Now there's only one trig identity that's going to turn sum of two things into one thing, one term, that is 1 plus tangent squared equal to secant squared. So we very much want this guy to be, this whole term to be a tangent square, not a tangent square, actually 25 tangent square. Imagine the 16x squared is indeed 25 tangent square. This will work out. Well, you can see if this is true, the 16 plus x squared of course becomes 25, matching the 25 tangent square. You factor out the 25, then you have 1 plus tangent square, which is secant square. Alright, so in this problem we're going to assume 16 along with x squared to be the desired multiple of tangent square, 25 tangent square. Well, if you solve for x, this just says x will be 5/4 tangent. You may have a number here, so if there's a number in the front, you just include in your square or whatever you have it there. Alright, so we come up with the trig substitution needed. Now do the substitution. (25 plus 16x squared becomes 25 secant squared. Plug in. And dx, well, just do the differential here. Dx equal to 5/4 secant squared d theta. 5/4 secant squared d theta. Now we already got a trig integral simplified to see how to evaluate it. 5/4 pour out. There's a 25 raised to 3/2 power. 25 raised to 3/2 power. Let's reach to half power first. Is 5. The 5 raised to the third power, 125. Secant square raised to half power first becomes the secant. Secant to the third power. There's secant square. So cancel out, there's only a secant in the bottom. Again, we got a rather simple trig integral here. As a matter of fact, it's very simple. Let's see first how we simplify this part. 5 and 125, we can cross out 5 with the 25 left on the bottom, so it's 100 on the bottom. The integrand 1/secant is cosine. So very simple. It's not surprising. Usually the expression we start out is not very bad. So with any of those three trig substitution, usually the expression here is pretty simple too. Well, integral of cosine is sine. Again, in this example, this is part 1, turning integral involving x to an integral involving theta, a trig integral, and then the integrate. So part 2 is again pretty simple in this problem. third part, that's to get rid of the theta. This problem will try a triangle again. Now, our substitution says x is 5 over 4 tangent. So tangent is 4x over 5. This says if we assume this to be theta, the opposite is 4x, adjacent is 5. Again, we use Pythagorean theory to figure out the third side, hypotenuse in this triangle. With the triangle constructed, you can find the expression for sine. So what's the sine? Sine is opposite over adjacent. Not adjacent, hypotenuse. So it's 4x over 25 plus 16x squared plus c. Yeah, this is the last step. Now, so far in these two examples, we've been able to using triangle to turn expression in theta to expression in x. This works when it's trig, like sine theta, tangent theta, cosine theta. Sometimes, depending on, I've not seen this kind of expression in those two examples, so I just want to point out. Sometimes we integrate the trig expressions, powers, combination powers. We may have, just say, I don't know, 1 over 2 cosine, 1 over 2 theta. The variable theta, say, is not inside any trig, just by itself. Then we cannot use the triangle to do it, because the triangle can tell us what we can have for sine theta, what we can have for tangent theta, what we can have for cosine theta. And if it's just theta by itself, what do? How are we going to turn this back to something in x? Well, if that's the case, we actually would have to rely on the substitution itself. In this case, we would actually solve for theta using brute force. So you say tangent theta equal to 4x over 5, right? So theta would equal to inverse tangent of 4x over 5. So this way we can still obtain some expression in x to plug in for theta, getting rid of theta. Alright? So let's see another example. And this is integral. The trouble expression is 9x squared minus 16 under square root. Most of the time, square root is troublesome. With the 2 or more terms under square root, that's definitely trouble, unless there's a straightforward substitution with a perfect supporting factor, that kind of thing. Okay, so how do we come with a substitution, trig substitution to work? Well, let's copy down the expression and stare at it. So we have something minus number, difference of 2 terms. The trig substitution we have in mind is secant square minus 1 equal to tangent square. So we want this term, the first term, hopefully to be secant square, precisely 16 minus secant square. This way we can factor out the 16. So this is our hope. We hope 9x squared equal to 16 secant square. With this, we can come up with the correct substitution, x equal to whatever. Alright? So let's see. Well, if 9x squared is 16 secant squared, plug in. Factor of 16. That's why you have to have 16 in front of the secant square, not just secant square. If you just get the secant square here, 16 square minus, if you just get secant square here, secant square minus 16 will give you nothing to work on. It will not work. So got to have the 16 to match the number back here, so we can factor out getting exactly the desired combination, which becomes tangent square. Alright, so now if 9x squared is 16 secant square, x will be simple algebra 4/3 secant theta, and that's our substitution. Plug in 4/3 secant theta for x, square root 9x squared minus 16 already simplified on the side, so 16 tangent square. The dx, well, dx is going to be 4/3 tangent square secant square d theta. So we're going to have a 4/3 tangent theta secant theta d theta. Right? Secant cross out. Actually 4/3 cross out too. So square root of 16 is 4. Square root of tangent square is tangent. Tangent is tangent square. Now we have again pretty simple trig integral here. Check again, tangent, secant cross out, 4/3 cross out, square root 16 is 4, square root of tangent, there's tangent square. Yeah. Well, how do we evaluate this? There's formula we can apply. Integral of tangent equal to whatever. As a matter of fact, we don't even need to use formula. We know tangent square is a secant square minus 1, so I can actually evaluate this integral with the simple integration formula. Integral of secant square is tangent. Integral of 1 is theta. This actually is perfect because I actually find an answer with the theta not inside any trig. That's what I was hoping to get. I was trying to explain. Okay, we actually have a problem that shows the case I was trying to explain. Okay, so I got the answer involving theta. The next thing is how to turn this back to an answer in x. Well, triangle. Well, at least triangle for trig expressions. Okay, let's see our substitution. This substitution says secant theta is 3x/4. Multiply both sides by 3 divided by 4. So our triangle is, what's the secant? Secant is a cosine, 1/cosine. So secant is 3x/4. So cosine is 4/3x. 4 over 3x. Adjacent over hypotenuse, that's cosine. With the Pythagorean theory, we can figure out the opposite side. So the tangent part according to a triangle is square root of 9x squared minus 16 over 4. Now this guy, well, it's not inside any trig, so we're not going to be able to use the triangle to do it. But like I explained, in general, we going to rely on the substitution. Secant theta is 3x over 4, so theta is take inverse secant. So theta is inverse secant 3x over 4. That's how we deal with theta variable that's not inside any trig. The theta is inside any trig, we have a triangle there. Alright? So this is a trig substitution technique with whatever combination. Number minus expression, you want the expression here to be something times the sign, of course matching the whatever number here, right? Sum, you want this to be tangent, of course with the appropriate number to match. Expression minus number, this expression should be secant with the matching a square. With this kind of assumption, like in this example, we assume 9x squared to be secant with the matching 16 in the front. Then we determine the desired trig substitution and do the substitution, turn this into trig integral, cross out, simplify, evaluate, get the answer in theta. We use triangle and sometimes the substitution, like in this example, substitution itself, just to turn the expression in theta to expression in x, the original variable involved in the integral. Alright, this is trig substitution technique.